and Lee will be monitoring the Q&A for you. So over to you, Lee or Nick.
Thanks, Lillian. Let me start sharing my desk. Okay, great. So hopefully everyone can see this. So this talk is basically going to be taking us through a number of facets related to data analysis on HL7 FHIR. So it'll be in 3 sections. My section is the first section, is just on the HTTP API that's in the FHIR specification. So if you're familiar with the FHIR API, then this should sound familiar, although hopefully you'll still get something out of some of the more advanced queries we do near the end. My name is Lee. I work on the IBM FHIR server, so I have a FHIR background. My co-presenters, Nick and Gigi, have a data science background. We all work together in Watson Health and IBM. So without further ado, let's kind of get into it. We've got a lot to cover. So, there's one thing I forgot to mention. The notebooks we're presenting here are open source and on GitHub. I added this link in the chat, and for tomorrow's Let's Build session, you will be downloading these and interacting with them the same way we are on today's call. Okay, so first, I just need to, open up my notebook, and I'm going to set up some imports and define a helper function. The most important thing here is this. So this is the base URL of our FHIR server. This particular instance is one that we use for connectathons. So this is an instance of the IBM FHIR server that has been loaded with some synthetic patient data from the Cynthia project. And so we'll be using this. You could, tomorrow try plugging in a different FHIR endpoint and see how the queries perform against a different endpoint. Okay, so the first section, the FHIR REST API. So FHIR itself defines a set of resources. So the API is defined on top of these resources, and they're kind of nicely categorized in the FHIR specification itself. And so you can see we have some clinical resources that we're going to be focused on today, but there's other realms, and this list is expanding, but comes with the FHIR specification. So then on each resource, oops, there we go. So on each resource, there's a set of HTTP interfaces. So the things you can do with each resource. So you have instance level, read, write, patch, delete, etc. Type level, and then whole system interactions. Today, we're mostly focused on data analysis. And so we're going to be focused on the search API. And then in the following notebooks, we'll be focused on using data analytics techniques against FHIR data, but not using the FHIR API. So here's a simple request to the metadata endpoint. So in the FHIR specification, there's the metadata endpoint to ask a server, like, what do you support? And so it's good practice for clients to introspect this. And so you can see we're working against the IBM FHIR server version 4.5.0. Security is kind of a key thing here. This is a fully open endpoint. This would not be realistic for patient data. You shouldn't do this, but for the purposes of our tutorial and our labs, we've got security turned off essentially. We just don't have enough time to go through all the security aspects. So we're focused more on the API for people that have access to the data. Finally, we have the supported resource types. And so you can see this server actually supports all the resource types in the base specification. And these are the interactions it supports for each resource type. And so we just have read, vread, history, instance, and search. And search is the one that we're going to be focused on. So now we get into the fun. So here's a query against the base endpoint. And if you put a /patient, this is the patient resource type, and perform that query, we get back a 200 OK. And what this is saying is, please give me all the patients on the server. You get a count, which in this case is a little over 32,000 patients, and you get back a page of results, which is 10. You can ask for the second page of results by following these links that are included in the response bundle. And so here, if we look at this next entry, we'll grab the next one and we'll resolve it. And so now we'll have the second page of results, which is also 10 entries. You can request a different page size by passing the count parameter. Here we've passed count equals 1, so we just want 1 result per page. And here's our response. So now there's just 1 patient resource in at the end of each request. Most servers will impose like an upper limit on this. I think ours is 1,000, so you can't have page sizes over that. Okay, so you can also specify a count of 0. So this is kind of interesting. Why would you want no results back? And the answer is if you're only interested in how many there are, you can specify a count equals 0, or equivalently a summary equals count. And so if we make this request, you can see there's actually no entries in the response, but we just get back that total. So this is really useful if you're just exploring like what kind of data exists on the server. And so here you can see we've got this number of patients. So now if we want to restrain the amount of data that comes back, there's a couple different ways to do this with the FHIR API. And so first, let's have a quick look at the patient resource structure. So this is from the HL7 FHIR specification. This is the patient resource. These are the fields it has. And if you notice, there's this little symbol here. If you've ever looked at the FHIR spec and wondered what that is, what it means is that these fields are the ones that get included in a summary. And so how you request a summary is you do a patient endpoint and then summary parameter equals true. And this will give you just the elements that have this little symbol on them. And if you need more control, most servers or a lot of servers will support the elements parameter as well. And this is a way of saying, I only want to get back specific elements from that resource. And so if we go ahead and execute these 3, we're going to look through the response payloads, look at the first entry, and print out the list of field names. So this is all of the field names. That's what you get normally. If you specify summary, these should match what the fields have this. And if you specify elements, you'd get back just the elements you asked for. We asked for ID and gender. Notice you do get back a couple extra things. It's at the server discretion, but they're encouraged to return all required fields, as well as fields that would change the meaning of the response or of the resource. So those are called modifier fields. So just a quick example, if we're going to do 100 pages per result, you can see if you specify just the elements you want, you can get back a much smaller payload, and on our server that'll come back faster. Okay, so now we get to some more details about the FHIR search, and each resource type has a set of search parameters that are defined. So these are the ones for the patient resource. And so this is the same page we were looking at earlier. It's just if you scroll to the bottom of that page, you'll have a set of search parameters you can search on. And so in our notebook, we're going to start with gender. So here's a search for the patient endpoint where gender equals male. And if we execute that, we get back our 200, and we have a set of 15,000. And this is going to be the first 10 results of that set. If we specify just the count queries, you can get an overview of how many male, how many female, and then this is an introduction to a new search concept called missing. So if we want to look for resources where the gender field isn't there at all, so it doesn't specify male or female or unknown, it's just rather the field is completely missing, FHIR Search supports that through this :missing parameter. In our data set, we don't have any of those, but it's a very useful technique for exploring the data. So now we get to search parameter types. So gender, in the example above, is a search parameter type called a token. So token search is used for coded values in FHIR. So that would be code, coding, and codable concept, but also for things like identifiers that have a system and a value. And so there's a few different ways of querying code values. The main thing is really you should be using the system and the code where possible, and not just the code. Some types, like the administrative gender, have a implicit system where it's not really needed because there's only a fixed set of 3 values allowed and they all share the same system. But for more open-ended concepts like diagnosis codes, you could do a search where it's the system and then this pipe character and then the code value. And so here, this will just show that we have a different way of getting the same results as above if we specify the system. In this case, okay, so that was all about the token search. So now we're going to go to a different search parameter type called string. So a string search would be for a non-coded text field that you're looking for a value to. So an example of that is a last name or family name search. So if we execute the search for family equals Smith, we get back a list of names. Note that some of these don't actually match the name Smith. So Smitham. And this is because text search in HL7 FHIR is by default, it begins with case insensitive match. So one thing we kind of recommend people that use the IBM FHIR server is that if you have an exact string match that you're trying to use, you should use the colon exact. This is the syntax again, what's called a search modifier. So now we're looking for a family name of exactly Smith. And when we execute that one, we should get back just patients whose last names have Smith. Note that some still have multiple family names. A common case of that would be like if the system has both their maiden name and their current name. Next up, we've got date search. So this is searching patients by birth date, everyone in 1984. FHIR date times can be year, month, day, time. And so it's very flexible. There's also a new concept here we haven't talked about yet, which is called a search prefix. And so a lot of times people get this mixed up with modifiers. So modifiers, you'd have that colon, and then it modifies the search parameter. Here, it's a prefix on the right-hand side of the equality, and it's going to modify the value. So here, EB is for ends before. This is starts after, and this is approximate. And so now we'll get patients that have a birth date before, after, and approximately around 1984. So the next section of search that we'll cover is reference search. So reference search, I don't have a good example in the patient resource. So we're actually going to go ahead and look at a new resource type called condition. So condition is like the problems or the diagnoses that a given patient would have. And this one has quite a few, and the most prominent reference here is the subject. So this is a search against all conditions that have a subject that matches this particular patient ID. And so this would be, like getting all the conditions for that patient. References are interesting because they can be relative like this. In some cases, you can omit this patient / if this ID only exists for a single resource type. So if that ID is not just for a single resource type, then you need to prefix it with this patient /. And then you could also do a full URL search. And so in this case, this is the same base URL of our server plus all that. So this is an absolute path, and it'll get the same results. As you can see, the result entries all match. Okay, so I want to leave enough time for my other presenters here. So I'm going through the last section pretty quick, but you can do some pretty advanced things through references. And so this is something called chaining. So if we do a chained search, we've got, this is all conditions with a code of diabetes and a patient reference where that patient is female. And so you can see we get a result set of 600 entries back. Similarly, you can do a reverse chaining, which is very similar, only it goes the other way. So now we're querying for the patient endpoint where patients have a given condition. Similarly, well, I guess a little different, we have includes and rev includes. These are similar in that they follow the same references. So they work on references in the same way. But in this case, instead of restraining the query, like constraining what we're expecting to get back, we're adding additional results And so if we execute this one, we'll get back not just the conditions, but also or not just the patients, but we'll also get back the conditions, or not just the patients, but we'll also get back their conditions in this one. So again, we've got these out on the GitHub site, so you can kind of finish going through this notebook. We'll be on tomorrow as well. And we kind of, the rest of this notebook just goes through a little sample scenario of introspecting, kind of figuring out which patients we have in the system. And at the very end of here, we're going to export those. And so the FHIR API is great. It can take you through a lot of stuff, especially if you have kind of a system where you have access to all the data on FHIR. The FHIR Search API is very powerful. But in some cases, you want to do kind of a deeper analysis on the data. And this is where the FHIR bulk data specification comes in. And so this is a sample request to our server that's going to say, please export all of the resources of type patient and condition. That comes back with a 202 saying, okay, we got it and we're working on it. And then this cell is going to actually just start executing, and it'll start pulling the status endpoint. It'll come back with a 202 until it's finally ready, and that'll come back with a 200 OK, as well as a link to the actual NDJSON files. So NDJSON files would be one FHIR resource per entry, and that's what we're going to pick up from the next notebook. So let me hand it over to Nick, and Nick is going to take you through, working with more traditional data science tools on top of the FHIR data. Thanks.
Thanks, Lee. So hopefully I'm sharing the right screen. So as Lee indicated, my background is very different. My background is machine learning and AI. And what I want to show you is that in order for you to effectively use FHIR data, you do not have to learn any new tools. So the demo that we're showing, as everyone in today's session, we're doing it out of the Watson Studio. And I didn't want to learn any new tools, so I would stick with the tools that I'm very comfortable with, as most of the data scientists. And to me, it's, of course, Spark. Anyone who works on a big data is probably very familiar and comfortable with Spark. So what we're going to do is we're going to pick up those NDJSON files that Lee just created. And there are some just basic imports at the beginning. We import the PySpark. It's a PySpark API. We're going to set up some of the cloud object storage functions and credentials. For tomorrow's session, we're giving everyone read-only access to those NDJSON exports. So you'd be able to actually practice and follow all of the steps that we're showing. And we're setting up some access to the cloud object storage. So this is IBM Cloud Object Storage. But NDJSON can be pretty much accessed at any environment, whether it's any cloud, whether it's your big data environment that you might have on-prem. If your laptop is powerful, you can probably do it on laptop as well. So we're going to set up some cloud object helper functions, the copy between the local file system and the cloud object storage and buckets. So just the very basic housekeeping. And then if I were to do it for the first time, I would actually want to see where my files are in a cloud object storage. What do I pick up? And after I've done that, it all goes back to a normal PySpark that every single data scientist should probably be very comfortable with. So first, NDJSON we're going to pick up is called R4 condition. Usually, it's a good practice for me to take a look at how many records I got. So this file looks like has 880,000 records. It took me about 22 seconds to pick it up. I'm just timing the operations to get the basic understanding of how big it is, what they have to deal with. So if you work with Spark, usually the good practice is if you limit to something sensible. So if it's just like 100,000 records, I would cache those data in memory. So the cache will allow me to quickly go through all of the consecutive operations without going back to disk. So they're going to be ultra fast. And then after I've done all of my exploration of the data, I would comment out the cache, the cache pieces, and just run through the whole notebook. So that's exactly what I've done here. I was first exploring the data. I had my cache on, then I turned off the cache and ran through the whole whole resource for patient, for condition, for observation, etc. Okay, so now first time I read the condition. I looked at the first 5 records, and you can't really make a lot of sense out of those first 5 records in Spark, because as you can figure out, it's deeply nested. So the functionality in Spark that allows us to look at them is called print schema. With the print schema, the indentation is reflective of the nesting indentation. And so that's how I was able to kind of go through them one by one and figure out the data elements that I was looking for. So I was looking at the variable, and the dot something would allow me to look at the right condition. So for example, for the first condition, I want to figure out which patient where clinical status coding code is active. So it's just you follow the indentation, say you want the first clinical status, then you want coding, and you want code. And that's dot is what you pretty much pass to your Spark. So here at the very beginning, I'm doing some where statements. I'm doing clinical status condition code active, verification status coding is confirmed. I want my condition for diabetes, so I had a specific code for that. And I also wanted patients that were date is limited to something, so I figured out people don't live more than 120 years usually, so it would be safe enough to pick up someone from 1900. So that's my where conditions, and then my select conditions refer to the variables I want to pick up. So I'm picking up my subject reference, and I'm going to create an alias for it, calling it a patient ID, and then I'll pick up the clinical status coding code, verification coding code. As you can see, those variables become really, really hard for me to figure out what they are, picking up directly from the condition resource, right? So by the time I pick them all up and I produce my Spark data frame, I said, well, yeah, that's fantastic. I have patient code, I have code, display, and first observation date. And even if I kind of look at it, it's really hard for me to figure out what it really means. And so that was kind of my first step. Yes, I can still print the schema of my data frame that I created, but it's really hard for me to figure out which element is, and just referring to them with those kind of indentation of coding that code is not something I found very user friendly. So my next step is I'm going to create some aliases. And alias in Spark is what allows you to assign a new variable name. And so the only change between the first one and the second one is that I am actually, as I'm creating and picking up the variables I want, I'm actually naming them something that would be more memorable for me. So here I actually have a condition status, verification status, SNOMED code, SNOMED name, and a first observation date. So typically, I don't have to go back to a data dictionary every time. Those names are kind of sensible enough for me, and I should be able to effectively use them in the next kind of consecutive steps of the model. But the pieces that are still actually not very convenient to work with, and so the example that Gigi will walk you through would be the machine learning and data mining. And so, it's actually, you don't want to deal with those arrays. They're not very straightforward, and the typical machine learning packages would not expect you to pass them an array. They expect you to pass the value. And so even though I'm happy with the variable names, I'm still not happy with what I'm getting out of it. And so my next step is, in addition to renaming the variables, I will actually flatten the data. And by flattening the data, I figured that most of the times, it's not, in vast majority of the cases, I only have one variable in this array populated. So in Spark, I would use the get item 0, and that gets me the first variable out of each array. And that first variable is what I can use to actually get me a proper flattened data set that everyone who is in AI, machine learning, or data mining would be comfortable working with. One variable, properly named columns, and one value for each of those columns and rows. So traditional square data that everyone is so accustomed to. Okay, so the next step would be going to the observation resource. The steps would be very similar. I'm reading the observation resource as an NDJSON file. I'm reading it from the bucket in the Cloud Object Storage. I am looking at number of records and I'm measuring the amount of time it has taken me to read it. So this one is a little bit bigger. It's actually about 20 million records, but you can still see that with the Spark parallelization, it only took me about a minute to read 20 million records. Not bad at all. The rest of the steps that I had to follow were the same. I looked at a very scary, very nested JSON. I figured out by looking at the data and consulting a data dictionary what would be the elements that I would want out of this JSON. And I would proceed directly with my third approach, which would select the variables I want, specific code. And then I would also rename and flatten all data to make it more traditional square. I also wanted to check the frequency of HbA1c tests in here. So what I'm doing here, I'm running my Spark aggregation query, and I just wanted to get something to look at the code frequency. I wanted to see, the first couple of records. I see a lot of tests for a given patient ID, so that was good. That was the results I expected. And then after that, I also wanted to take a look at, what is the average number of tests the patient is getting. So after I summarized the values by the patient ID, I did my typical, count, mean, standard deviation, minimum and maximum values. And that was just a, embedded PySpark describe function. After that, I looked at exploring the patient resource, still the same steps, read the data, looked at the, how much time it took, appreciated the complexity of the raw data. I looked at the nesting of those formats. They, one more time, they look a little scary at first, but then, the scariness goes away once you figure out which variables you want and you're flattening them. Okay, so what I'm doing here is I'm creating the patient resource by selecting only the columns that I want and giving them the new names. I am looking at how many variables, how many records I have for patients with diabetes condition, counting them. I'm comparing them with all of the patients, so I know it's a lot smaller number, 8,000. And then what I'm doing is I'm joining my typical, database join, just using the PySpark code. I'm creating my patient with diabetes by joining patient with joining the condition diabetes. And that's my kind of first version of the merged data set. I have a patient ID, all of the data, birth, gender, status of the condition, everything else, SNOMED code, and first observation data as well. The next piece we're going to do is we're going to actually create a LPR, or longitudinal patient record. All I'm doing here is I'm creating a couple of variables, right? I'm creating the condition status, verification status, SNOMED code, SNOMED name, and selecting the variables I want. So previewing the first 5 records for this data frame. And then I'm creating my condition target as well, so which tells me patient ID, target code, name, and a first date. And then I'm getting all of the other conditions for the patients, so I can join them all together and create a kind of proper LPR. So now I have a patient ID, status of the condition, and all of the other conditions like hypertension, chronic kidney disease, diabetic renal disease, all of those things. And I pick up what was the first observation date and the last observation date for each of those conditions. The next step would be to only restrict those to the relevant comorbidities and complications. So these are just the codes I'm passing. And I say limit the data to those codes only using the EasyInt index. And after that, I can review where I am. So this is the data that I really want to get. That's my kind of first, my first step in the creation of LPR. And then what I'm also doing here, I'm creating my first and last date of each condition. So I'm just grouping the data by patient ID, target code, target name, SNOMED code, and a SNOMED name. And with that, I'm creating minimum, maximum date for each of the observation dates. And I'm also taking the minimum of the first observation date for a diabetes condition, right? So these are for the targets. This is for my original variable. And the only other thing I need to do to have a proper LPR would be to add the patient birth date and a gender. So I'll do one more join, and now I have a proper LPR that has my patient ID, birth date, and all of those information as a different rows. And the only final thing I might want to do is I would want to convert my row-based LPR and a column-based LPR. So it's just literally one line of code. I'm just creating a PySpark pivot, and I'm pivoting all of the condition variables and dates into the separate columns. So depending on how you want to build your model, either one of those might be more convenient. So this one was more user-friendly for kind of if you want to iterate over the records, and this one is more user-friendly if you just want to build a model and pass them as a set of predictors. And the only thing I have left is I'm going to be saving them into a cloud object storage, and I'm going to be passing those saved data frames directly to Gigi so she can demo her machine learning applications on top of this data.
All right, thanks, Nick. Let me grab my notebook. Although it won't let me. Give me 1 minute. It really isn't letting me share my screen. Let me at least try this then. Can you see it? Okay.
Yes, we can.
Good. Perfect. Oh, wow. Good day, everyone. I'm Gigi Yun Reid, part of IBM Watson Health. My background is actually in operations research, but in the last 10 years, I spent most of my time in healthcare data science. So it's very exciting as we move in the era of having our data more easily available in the FHIR layout. So in this notebook, I will show you how I take the output of what Nick has prepared, right, in a set of Spark Parquet files and bringing it together, do some statistical analysis and build some machine learning models. For the interest of time, I'm going to skip the setup. It's very similar to what you've seen in Nick's work, with the exception of adding some machine learning packages. We bring in the data, which is one of the files that he saved in calls, which is LPR row. Just a quick check to make sure it looks exactly the same. You will notice that a patient, for instance here, a patient can have multiple records, right? This female patient who was born in 57, each record represents a comorbidity that the person has had. So in this case, the patient has hypertension, neuropathy, and so on. And you'll get a few dates here that Nick had prepared for us, right? The first date is the date of diabetic onset. So for this patient, her first onset of diabetes is back in 1979. It seems like she's gotten hypertension earlier, which is this first observation date. As of 1975, she's gotten hypertension prior to getting her diabetic onset. But there's other conditions that came a bit later in the 90s, for example, neuropathy and diabetic renal disease and so on. So now we have a kind of handle of what the data we're dealing with. Each row is a patient and his or her comorbidity. Then let's take a look at this SNOMED code system, which I think was passed through, and you've seen it in both Nick's work and Lee's work, but it's helpful to just store this as a dictionary so that you can have a quick look out to know for the specific code, which condition you're dealing with. Okay. And I think like any data science work you want to do, you always want to start with understanding the science behind it. And since we're in healthcare, we're going to spend some time understanding the clinical science. So here I just quickly included a couple of examples. You may wonder, how did we come up with the list of codes, right? The set is actually come from this paper, pretty recent paper that studied diabetic comorbidities. It's pretty recent and pretty comprehensive. So we picked it from this list. And if you look at different papers, there will be different lists. A good practice to do is to survey some and come up with a list that your clinical advisor is comfortable with. Our goal here is to think through, given a diabetic patient, how would the patient's disease progress over time? So we take a look at the complication that's common around diabetic. CDC has a nice list. pretty consistent actually if you look at different countries, public health agencies for diabetes. In our case, we have decided to take a look at the disease progression to something called neuropathy. It's a disease that relates to the nervous system. A mild case of it, you'll get numbness in your fingers or toes. In case that progress severely without well-controlled blood sugar, you can lead to the need to amputate your foot, and you can also have just implications in the overall nervous systems. Before we go on and start doing some modeling, we want to take a minute and say, hey, is the prevalence of the different comorbidities sensible? So just did a quick count. Hypertension is the most common one and so on. So it seems pretty reasonable, right, given the size of the data set. So now, okay, then we feel like we can move on. Some just cleanup work about the data type. And then we created a few features, additional prediction features to help us better understand the patient and describe them. Right. One thing that I created is this notion called onset age. It's how old the patient is when he or she got diagnosed with diabetes. And taking a look at that, most of the patients in our data set didn't get diagnosed until they're closer to adulthood, and it can spread over quite a wide range of time when people find out that they do have the condition. Another notion that we want to include as a feature is the time difference between diabetic onset and the complication onset, or we call comorbidity onset. In this case, for example, for this patient, she got diabetes in 2009 in March, whereas gotten hypertension back in 1983. So it's 26 years apart, negative meaning the complication occurred before diabetes. And the neuropathy case is the other way for this patient. So this is going to be pretty core to how we set up our modeling cohort, the notion of a cohort and how we defined it. We want to dig a little deeper on the timing of these different events. We don't want to include things that are not sensible. So this is just a plot of the comorbidity onset day in relation to the diabetic onset day. 0 is here. So in this case, a lot of patients got the asthma before the diabetic onset, and some get it after. Seems like asthma, it's an exception. And you can see it's just a list of conditions, and most of them tend to onset after the patient finds out he or she has diabetes. Okay. And then also just to understand the timing of the data, you want to know when the data starts and ends, so you have a good handle. So this data set spans a very long time. And I think it's the nature that we actually pull in the data from Cynthia, which generate, a lot of you may know, which generate synthetic patient data. For that specific algorithm, it takes patient from birth all the way to death. So you can see that the time range tends to be very wide. If you're dealing with a EHR data set or a administrative claims data set, it's probably going to look different. Actually, that's a comment that I should make. Some of the observations you're seeing in this specific example may not make perfect sense clinically and may not reflect data you would likely see in the field. So you would notice that I barely did any data cleansing, any data quality control, and any of that sort, because we are benefiting from the cleanliness from a synthetic data set. So just a quick note. Typically that take 2/3 of the notebook, whereas the machine learning part is a short part. Okay, anyhow, the next step is, now that we have our data in place, we know we have sufficient information to build a model. So just let's get the groundwork laid out, right? Let's be very clear what we're trying to predict, what's going in as input and what's going out as output. The model that we want to build, as an example, is the likelihood of a patient developing neuropathy 5 years after diabetic onset. So imagine you can use this in a patient encounter. Patient comes in and you just learn about the diabetic condition, you want to counsel the patient or help the person with care management. And depending on how likely they will get neuropathy in the near future, in this case, 5 years. At the point of that healthcare encounter, you wouldn't know what happens after the onset. You only know what happened before that. So we want to be fair. We only want to capture input features that you know at the time of onset. In this case, it's demographic data, age, gender, and some other comorbidities that are derived. Nick has also prepared some HbA1c lab results, which is the diabetic blood sugar test. I don't have it included in this notebook yet. But one can imagine that you can also bring that in and say, hey, based on your first HbA1c test result, this is where you are. You can also help the model to be even more predictive. In terms of prediction target, in this case, it's simply if the patient is a binary. Did they get neuropathy or not in the next 5 years? First and foremost, you do with any cohort analysis is you want to ask yourself, do we need to include everyone in your data set? Just because the data is there doesn't mean that it meets the needs of the model. So you will see here there's a few selection criteria. I won't walk you through in details. They're pretty classic ones that you want to exclude patients that fall out of those criteria range. So you put them together, your data set will run from over 7,400 patients to closer to 6,800 patients. Now we can do some cleanup work and get all the input features organized. One of the things I've done, similar to what you may have seen earlier in Nick's notebook where I did a pivoting, where now I have the data structure so that there's a record for each patient and all the patient's information is in the columns. There's a lot of NANs because those patients never gotten that specific SNOMED condition. So, all right. And then some encoding, I'm turning, for simplicity's sake, I'm turning the years differences into simple binary yes and no. Did the patient have that condition before the onset and so on. Also, created some new features, just counting how many comorbidities the person had before the onset and so on, checking on it and make sure things are making sense. And just a few, data descriptive analysis. Kind of best practice, normalize some of the non-sparse data. I wouldn't worry about the binary data already, but here I normalize the onset age of the patient and the number of comorbidities the patients have. Now I have a nice and neat data set with the additional features that I created. Then we can get into modeling. I only have a couple minutes left, so let me just highlight a few things of interest. First, you want to prepare your data set and split it into train and test data set. You wouldn't want to train your model on the entire data set because you want to set some aside to test to see the performance of your model, to be fair. Best practice is to really understand each individual feature's impact on the prediction target. So in this case, we did some univariate analysis. I tried out a few modeling framework. There's dozens, if not hundreds of them. Logistic regression is a nice, simple one. It's linear, but it's very easily interpretable. You don't have to run any more explainability module on it. You can take a look and understand what features are important. Support vector machine is also very nice. There's some nonlinear option. Also tried out some decision tree classifier. For the interest of time, let me take you to just some of the results. I'm going to jump forward a little bit. So this table is the output of the logistic regression result. It's what we call a feature importance table. You could see the list of features in descending order of the impact they have on the logistic regression model. The number of comorbidities tends to be the strongest predictor. And then this is the famous confusion matrix. And the way to think about it is this is the row is the predicted results and the columns are predicted results, the rows are the ground truth. So in this case, you can see that the model is doing pretty well. If the patient will not get neuropathy, the model pretty much capture all of them. In the cases of patients who do end up getting neuropathy, the model is getting about 80% of them. 85 out of 106. There's all sorts of reports that you can generate. For the interest of time, let me kind of move forward to show you the best model. Yeah, it's at the very end, which is the decision tree classifier. And you can see that calling this decision tree package from scikit-learn, it does perform really well. It didn't, it made a couple small mistakes with the false positive, but it's doing really well in terms of false negative. And you can see the classic ROC curve as a result. It's a nice big curve up here. It's doing a really good job. With the tree, it's not like logistic regression. You can take a look at feature importance easily, but there are options where you could take a look at what the decision trees end up looking.
I'm sorry, Gigi, to cut you off, but that's all the time we have for today. So thanks everyone for the attention. And please note that the Q&A will also be still open after this session. So you can still post your questions to these speakers. And thank you for presenting. And if everyone wants to rate the session in the WUFA app, then we would be very happy.
Yeah, there's a Let's Build session tomorrow. So if you want more, we can work with you on it. Thanks.
Okay.
Thank you, guys.